Hello, and welcome to your really chill after lunch session. So I'm Matt Butcher. I'm the CEO of a company called Fermyon. That's Justin.
Hi, I'm Justin Pflueger. I'm a customer success engineer at Fermyon.
And so what we're going to do today is we're going to do a workshop on running WebAssembly workloads inside of Kubernetes. We're going to kind of step our way through the process. But to kind of kick everybody off, I'll give you a little bit of background information about kind of what this WebAssembly thing is, why it's interesting, and why suddenly it's kind of all over the cloud space. And the way I like to think about sort of the history of cloud computing is that we all got started off with virtual machines, right? This bookstore sort of started making it really easy for us to rent their extra compute capacity. That was AWS, allowing us to upload entire images of an entire operating system to their hardware and then run it. And that was kind of the first wave of cloud, right? That was where we all kind of started. Fast forward a little while, and we were all getting frustrated with the fact that these giant virtual machine images were hard to push, hard to manage. Developers were having a really hard time building applications and then putting them inside of these big VM images and then doing deployments well. And along comes a second technology. I think many of you probably saw Solomon talk this morning in his fireside chat. Solomon and their PaaS company sort of stumbled their way into building up a really amazing way of packaging up applications into containers and then deploying just these containers. So I think of like a container is sort of like a pie-sized slice of a virtual machine. It doesn't have the kernel, it doesn't have the drivers, but it has your application and a little bit of the file system and all the stuff you need to make your long-running servers run. So that was kind of the second wave of cloud computing. And out of that, we got orchestration layers like, Fleet and then Mesos, and then Kubernetes came and sort of ate the world. And Kubernetes is kind of the default orchestrator of choice now. And that kind of new way of orchestrating workloads by pushing containers into a container orchestration platform and having it sort of shunt around your containers to the right nodes, that was kind of the second wave of cloud computing. So along the way, Amazon and then a few other companies introduced another interesting way of building applications in this environment. Amazon was trying to use up some of its spare compute capacity, and they realized, well, what would be ideal is if they could sell like compute by the second, so that when they had a spare virtual machine space sitting out there, they could spin it up, run something, shut it back down, and free it up so that somebody else could get it and pay more to run it for a longer period of time. This was about 10 years ago when they first introduced Lambda. So the idea with Lambda was, instead of running a long-running server, you just write an event handler. A request comes in, Amazon spins up your Lambda instance, runs it to completion, shuts it down, frees up that VM, and they can use it again for another customer. So it's somewhat ironic that when Amazon came up with this, the idea was that they could use this just to eat through their spare capacity. Well, according to Amazon, in 2022, they executed 1 trillion Lambda requests. That's 1 trillion times something spun up, ran to completion, and shut down per month. So what we can learn from this is it's not so much about making Amazon money by eating up their spare compute capacity. It's about the programming model. That programming model is actually pretty fun and pretty nice, because for us as developers, all we have to do is write a function that takes a request, does some stuff, and returns a response, and we can be done. Now, Lambda wasn't necessarily built to be the sort of high-performance, front-endy kind of application environment that us as web developers or REST API developers or service pipeline developers would really want. Right? A Lambda function tends to take about 200 to 500 milliseconds to start up. It's actually, the reason behind that is because it was built on the first wave of cloud computing, right? The virtual machine layer, and it's still dropping workloads directly onto virtual machines. So fast forward a few years, Justin and I and many of our colleagues were all at Microsoft. And we were doing research into how to sort of build a really fast, really high performance serverless style environment. And the conclusion we came to was that virtual machines can't get much faster than they are now. Containers were still taking about 12 seconds to start up, and the way these things were working is you'd pre-warm these things and queue them up, and then you'd have to install the application right when the request came in and then execute it. And we couldn't figure out a way to make that work terribly faster on containers than it was on virtual machines. So we came to the conclusion that what we really wanted was a third kind of cloud runtime, something that would sit alongside virtual machines and containers, but whose runtime characteristics was really fast startup, cross-platform, cross-architecture, really good security sandbox, and pretty good support in the ecosystem already. So we weren't asking people to start all over from scratch and have to build new things in a new language. So, you know, as every R&D team does things, you know, we tried building our own, we tried a couple of other things, but we discovered WebAssembly and went, oh, this is a really good runtime. So WebAssembly, when it started, it was intended to be a browser technology. And the original design goal of this was, we got all this legacy code written in C, C++, other languages, and we also know that JavaScript isn't a super high performance language. So what could we do to make it possible to sort of augment JavaScript's features by adding libraries that were written in different languages, like maybe C or Rust or something like that? And so some developers at Mozilla came up with this idea for WebAssembly, pitched it to the developers at Apple, at Google, and at Microsoft, and they formed a consortium and built the WebAssembly specification out of this. So originally the idea was you could take this old C library from, you know, I know of one from the 80s that was actually compiled to WebAssembly, run in the browser, so that you don't have to rewrite your C code into JavaScript where you could access it. Or another cool case of this was with Figma. Figma, people familiar with Figma? High performance vector graphic program that runs in your browser. Why is it high performance? Well, part of the reason why is because big chunks of the logic are written in C++, compiled to WebAssembly, and then JavaScript interacts with that WebAssembly binary. So WebAssembly was kind of a good and cool technology for the web browser. For those of you who remember back when Java applets and ActiveX and Silverlight and some of these other technologies were around, all of those were kind of proprietary ways to try and get at some of the same things, but this is an open source, open standard way of doing kind of the same thing. So here we are at Microsoft trying to find the third wave of cloud computing, going, okay, there's got to be this sort of like ultra fast spelt runtime that we can run serverless functions on. And we run across WebAssembly. And we're going, well, this is interesting. All the characteristics that are good for the web browser are the ones we care about. You know, we all know as web users that we are incredibly impatient. We do not like to wait for websites to load. In fact, some research suggests that we're sensitive at the 10 millisecond E level, but for sure, Google is sensitive at the 100 millisecond level, right? Your search engine rankings start to drop if it takes more than 100 milliseconds to deliver your first byte from the server to the browser. And so we knew kind of that performance characteristic of WebAssembly was going to be important. The security sandbox model for WebAssembly was the second thing that was really good for the cloud, right? On your browser, we run untrusted code all the time, right? Because we're surfing the web and everybody's downloading JavaScript and they're running it inside of our browser. And so the sandbox for the browser is very strict. It prevents people from being able to access your file system or do dastardly things on your system. The WebAssembly sandbox is even a little bit stricter than the JavaScript sandbox because they had to make sure that the WebAssembly sandbox couldn't be used to attack your JavaScript code. So they built a really nice secure sandbox. And we're looking at that going, that's pretty much cloud right there. We want high performance. We want a really good security sandbox because then we can drop the security sandbox environment on the cloud in a gigantic runtime and run thousands and thousands of these WebAssembly modules side by side and not worry that they're attacking the host or attacking each other. So, you know, we looked at WebAssembly, thought, hey, this is a really great technology. Let's start working on it. So at Fermyon, you know, we started Fermyon and began building an open source project called Spin. And we're going to be using that a little bit today. Spin is essentially a nice, easy developer tool for building WebAssembly-based serverless functions. You can use a variety of different languages. I think I'm planning on sticking to TypeScript today, but Rust, JavaScript, Go, Python, a number of other languages work there as well. And if you start on the workshop, you can kind of pick whichever language tickles your fancy, and we'll see where we go from there. So Spin's the developer tool. We'll walk through that one first. And then you kind of need a place to deploy them, right? To deploy your applications. So we provided two different routes to do that. The first one is there's a place called Fermyon Cloud. It's our hosted cloud platform. A big chunk of it runs on Civo. I'm actually talking tomorrow about how we're doing our AI inferencing using Civo's GPU services. But Fermyon Cloud runs there. I think we'll walk through it maybe pretty quickly here. Super easy to finish your application and do spin deploy and have it up running on our architecture in the free environment and be able to test it out. So that's one place. The other place is inside of Kubernetes. Right? And one of the big advantages here, and one of the reasons why it's so important to us to be able to run these applications in Kubernetes, is that if you're using something like, a Kubernetes cluster and then sort of the off-the-shelf, Lambdas or Azure functions or things like that, you're essentially managing two very different kinds of compute. And we thought that by bringing the spin runtime inside of Kubernetes, essentially you'd be able to manage your serverless functions as pods, not much differently than you'd manage any of your containerized workloads. And it means your containers and your WebAssembly can kind of work side by side. So that's the last two parts of this workshop that we'll cover. We'll talk about using K3D to install locally, and then we'll talk about running this all on top of Civo inside of Civo's Kubernetes. So that's where we're going to go. Did I miss anything?
I don't think so.
All right, so we'll start it off. We'll kind of talk back and forth through what we're doing. Then we'll pause periodically for people who are following along with the workshop. But the thing right now is to steer on over to github.com/fermyon/workshops. And then click on the directory wasm-and-containers. And that kind of outlines the flow that we're going to go through in this workshop.
And if you have any questions at any time, just raise your hand. I'll come around and help you get unblocked.
Is that big enough on the monitors on the side so that folks can read it? Okay, hearing mainly yes. Haven't heard a no. All right. You want to walk through the setup part?
Yeah. Cool. So as Matt mentioned before, Spin is our CLI tool. It's our developer tool. It's how you kind of interact and build these serverless functions using WebAssembly. So the first thing that we do here is we want to go install Spin. If you're on this page on GitHub, you can click on this link. This is just the Spin link. So if we go over to projects and Spin, oh, we're already there. It's not projects, is it? It's documentation. Resources, documentation, that's where I wanted to go. And then down here you'll have Spin, and on the left side you can go to install and pick whatever operating system you're on. Follow these instructions to get Spin installed, and we'll give you a couple minutes here to get everything installed. If you guys have any questions in the meantime, just holler.
So if you're on Mac, probably the Homebrew is the easiest. Or,
Yep.
Well, curl bash is probably always the easiest, but Homebrew is the easiest, safest. Do you want to talk through how plugins work?
Yeah. So in order to kind of completely compile from WebAssembly into Spin applications or from your source code into WebAssembly, especially for interpreted languages, we need to do a little bit of extra work to put the interpreter inside of WebAssembly and then load up your code into the interpreter. So for different programming languages like Python and JavaScript, TypeScript, we built these a plugin system into Spin.
I'll try and list them out so people can see while you're...
So Matt's already got it in Spin installed, and Spin plugins list will show you all the different plugins that you have, as well as all the different versions. So the two that you'll want if you choose to go down the JavaScript, TypeScript, or Python route are JS2Awesome and Py2Awesome. And what those do is kind of load up the interpreter and compile it into WebAssembly, and then your source code actually gets included as an asset. Question?
Yeah, move the screen this way a little bit so we can see like the first.
Oh, yeah. Let's just get cut off on that one screen over there.
What?
Oh, okay, well, never mind. It's just that one screen.
Oh, yeah.
Thanks, man. Appreciate it.
Yeah, you bet. Cool. Question?
With something like Rust, do we have to swap if we're using Warp for the API endpoint? Do we have to swap it to the HTTP endpoint you get from Spin?
So you're using Warp as the HTTP server framework, and so since you don't run a long-running server, you don't necessarily need something like, well, nor does it make sense to run something like Warp. But there are, so what, I'm gonna have to look it up. There is a Rust router that functions very similar to the Warp router. And actually, well, there's one for JavaScript, one for Python, that just maps the API request to a particular function. But you wouldn't necessarily need Warp in all of its entirety.
So the way this over testing works is it downloads a Monix model, sorry, a state tensor model from S3. Spins up a long-running server, and we use that for inference. So we have to kind of change the architecture a little bit to basically either download with the container and just do like a one-time inference and then shut down.
Yeah, and so the way we tend to do those is to package all of the assets up in the WebAssembly so that it gets deployed, or to try and pull it from a close source instead of a far source if you want to do it that way. Do you know what models you're using?
It's a variational autoencoder that's trained on it.
Okay, yeah. There's also part of this, and this is jumping out of order. I'll talk about it a little bit more tomorrow, but we support running models in Fermyon Cloud. They run separately on a scheduled, basically GPU scheduler, and then you can just write code that does the inferences and hits the models in the back end. But the only ones supported by default are the Llama variants of it, so it probably wouldn't help you too much there. Yep.
Cool. Does anybody not have Spin installed who wants Spin installed? All right, well, we'll continue then. Yeah, so like we said before, just if you're following along these instructions, you can run a Spin plugins install cloud. So that'll be kind of our remote development environment that we'll get to here. And then JS2Awesome and Py2Awesome if you choose any of those two languages. If you're using Go, you'll need to install TinyGo. And there's links to that here. You can also use Rust if you're familiar with Rust. Do you want to go through the new?
Yep. All right, time to write an application. Where did my terminal go? There we go. So we've got our spin command. We can do spin new to create a new application. What this is going to do is set up all the stuff that we need to build a WebAssembly binary. We're going to call it my application, which is so creative. And then we're going to start with a template We're going to use the HTTP TypeScript template. So the command is spin new, and then the name of the application, and then the template that I'm going to use. Thank you. Can you sit behind me every day and fix my typos before I commit them? So I'm going to run that command, but let me, and then it's going to take a description, a default path, and we'll walk through that in a second. But if you want to try different languages, you can run spin templates list and see all the different languages there that you would be able to write them in. Of those, the SDKs for Go, JavaScript, TypeScript, Rust, and Python are the more feature complete ones, the tier ones. So I recommend, kind of sticking to those languages for now. Actually, the Prolog one, which is a community maintained one, is also fairly well featured, but I don't know Prolog very well. So, okay, so we created our new My Application directory here, and we can very quickly look at it and see. I'll use tree here. We got a README file, we got a package.json, which is typical for any JavaScript, TypeScript thing. If you were doing this in Rust, you'll see your cargo toml file. If you're doing it in Python, you see, I forget which package manager we use for Python.
Requirements?
Might be, it's the other, the newer one, but maybe I'll try it in a second here. Webpack, tsconfig, all general stuff. The one special file here is the spin.toml file. So if we take a quick look at that, it's a short markdown file that basically provides information about our application. So I'm going to really quickly diverge into one very small piece of terminology, and then we'll get back to coding. In WebAssembly, you build components, and components can interact together with each other. So, it's a far more sophisticated demo, but you can literally build a library in Python, build a library in Rust, and have the two of them talk as components with each other. But the way that Spin works is that Spin can map a component to a route. And so HTTP request comes in, and we see this route line here, and it says /.. which means anything under slash. But we could do something, more specific like /hello, and then it would listen to hello. We can map multiple components to multiple routes. And the components don't have to be in the same language. So we could write one spin toml file and have an API endpoint written in Rust, one in Python, one in TypeScript, and have them all kind of work side by side. However, all we're going to do today is just write the one kind of default one. Oh, that's a good idea. We'll add a Python one. So there you go. Now we have a single application that has an HTTP component and a Python component. We'll have to change the route on that, otherwise they'll both try and answer to the same thing. You're going to do a code-n dot.
I am not used to anyone else's terminal.
Sorry, I know. Everybody's terminal is... So here's our VS Code editor.
I'll just blow that away.
So Justin added a Python component. Now we're just going to remove it back out so that everything is nice and tidy. But it is fairly straightforward to add multiple ones there. So I'm going to... let's see. Let's take a look at the application that we wrote. This is a TypeScript serverless function. So, the TypeScript format is a little bit robust, but basically we have a function name handle request, and it takes a request and it returns a response. So very basic kind of thing. Request and response are both HTTP objects. So just about any framework and just about any language you've worked in has some pattern similar to this. Gets a request, returns a response. So all we're returning is an object literal that says, sets the status code to 200, sets the content type to text plain, and then we're returning a message. So I'm going to go ahead and show the build step while y'all are playing around with this as you go. But Spin, so every language kind of would have its own set of tools that you would use to assemble a WebAssembly binary. Spin just sort of abstracts that all away. So inside of this build command, we can see it runs a spin pytawasm command. But all we have to do from the command line is write spin build. Oh, before I do that, I do need to do the obligatory npm install because this is a TypeScript project. So npm install is just going to go install all the dependencies. Otherwise, when I go to build, it'll have a missing library and complain that something's not working. So npm install ran. Now I'm going to do a spin build. And so at the end of the spin build, so I started with that TypeScript file, right? At the end of the build, there's a target directory. If I ls the target directory, I will see my application.wasm. And then I'll show you the step to test this out and then give a couple minutes for people to catch up, ask questions, things like that. So we created a new one with new. We ran a build to build the application. Now we're going to test it locally, just running spin up. That's going to start a local listener that's listening at 127.0.0.1 port 3000. And if I open that one up, sorry, that text is tiny. We'll see the hello world text that we just generated. So we'll give a minute here for people who are playing around with this to try things out. Let us know if you have any questions. If you're sitting not trying things out and have any questions, feel free to throw them out here. General questions, performance questions, anything like that. I can answer those as well. Yep.
Accessing different libraries, different components.
Yep.
So is it all done within one Lawson, or one can do like
Yep.
Lawson written in Rust that can access libraries,
Yep, that's an excellent question. So the question was boiled down, and correct me if I get anything wrong here. How does this work if I'm using libraries from different languages? Is it all one big WASM file? Am I pulling things in? How does that work? So there's the easy base case, which is the one that we're doing here now, where you compile a single binary that's just a WebAssembly binary that pulls in its libraries from the local language toolchain, right? So as we did the npm install here, it's just pulling in JavaScript files, right? Say I want to do something where I have a Rust library and I want to write a Python application. Essentially, the way the two communicate is you add, so you've got your WebAssembly binary, and then you have a description file called a WIT file, a WebAssembly interface type file that basically is like you'd see with gRPC or any of those sorts of interface definition languages, describes the imports and the exports. And currently, the way things work is you use a tool to sort of combine them all up into one WASM binary and then execute that. But you'll have a WASM binary here, one here, the WIT files, and then you run what's essentially a linker, and it links up these binaries from one language to another. So the reason why you get cross-language portability is because they're all getting compiled to the same bytecode format, and it's actually bytecode import, or it's bytecode compatibility, right? So that's sort of the mechanics behind it. In practice, right? How do you do these things? The tool chain for this stuff is evolving very rapidly. So at this point, everybody's kind of recommending, well, you pre-link your binary, you deploy that binary, the pre-linked one. It won't be very long until Fermyon and others start supporting being able to do sort of last deploy time binding or per invocation binding, and you can literally choose your libraries as you go. So why would you want to do that? Imagine you've got a case where you've got your central app and you've got this library over here that's doing, say, some kind of database stuff. And so this is my component for database. This is my component for my app. When I spin up the app, it links to this component using the database stuff, and I'm getting, just regular database calls. Now, something goes wrong here, and I don't really know what. And it only happens in production, of course, because these bugs only happen in production, right? It should be possible to deploy a Shim module that sits between this one and this one, and can help you debug it, basically dump a query or something like that and give you some visibility in there. Or another example is, say that this one has an unpatched vulnerability and you know that vulnerability. You can write a piece of Shim code that says, I'm going to intercept anything that goes against that vulnerability and patch it here in my Shim. before it goes on and hits the upstream module. Or observability is another good example of this, where you just say, this thing doesn't ship with any metrics or observability, so I'm going to add, a module in here. Or, the more I talk, the more use cases I come up with. I might have key value storage, which is a fairly simple string, store get kind of thing. I might swap in and out different implementations of the same thing just by module. So in any of those cases, as we get going, right now you have to make that decision up front. But the reason is just that the tools are in active development. Within a couple of months, you can make that decision at deploy time, runtime, and that's where it gets very, very interesting.
So the first case sounds like I'm doing it with two blossoms that are compiled with different languages.
Yeah.
With interface definition, right?
Yeah.
And then the second phase, and I'm the one that mentioned on the Discord server, the logics.
Oh, yeah.
That's got, it can file a blossom that's its only target, but it also can pick up a C library, correct? I believe it can
If
call C libraries directly.
so, in our sandbox, it wouldn't let you call a C library unless you compile the C library to WebAssembly, which a lot of them can do. But
So that's kind of what I'm trying to get to, is how do you do that? So is it like in the WebAssembly or it's part of the compilation?
yeah. And that gets us one more step further into the more sophisticated part, right? It should be, if you can expose something over a WIT binding to the underlying substrate, whatever, the runtime, then you should be able to run other things. So for example, our key value storage implementation is written in Rust, exposed as a component through the runtime. And then when you use key value storage inside of Fermyon, it's actually running Rust code, it's running, machine language compilation of Rust code and not a WebAssembly binary. But now we're getting really deep into
For my specific use case, one of them is I want to take a WebAssembly and access libptp.so, which is a C module.
Yeah, and in that case, you end up, because you're dealing with native code, which is outside the WebAssembly sandbox, that's when you have to use what's called a host binding, which would actually be exposing it directly inside of the WebAssembly runtime. So you'd go to the spin library, for example, and look at the cases of how we did it with LLM inferencing and database and stuff like that, and pipe it out that way and expose it via WIT bindings into the runtime. Okay, so that was a side note from where y'all are going. Anybody have any more questions about getting this basic spin app up? All right, we'll keep going there, and then I'll circle back and do questions again in a bit. That's the wrong, where did I put the workshop? There we go. All right, so we've created a new spin application. We've looked at the manifest. We've done spin build and spin up. You want to do a Fermyon cloud deploy?
Yeah. Yeah, so one simple way just to get this kind of deployed to like a publicly available endpoint is to use Fermyon Cloud. It's a free service. Will always have a free tier, correct?
I like how, look at Matt. Yes, Matt nodded.
Look at the CEO. Yeah, so one way to do that is just spin cloud deploy. And if you're in the directory of a spin.toml, it'll take that spin.toml and it'll deploy it to our cloud. And it'll provision a URL for you to be able to hit your app.
There it is.
And here it is.
So that's a great, easy way to get an application up and running where other people can see it very quickly. You can also map domains to it. So if you're running something like a website or a web service, you can map your domain to your spin application. Inside of Fermyon Cloud, let's see, key value storage is supported, and SQLite style databases are supported. So all of those are just totally built into the system. And then AI inferencing is supported if you're using the Llama 2 models.
Great. So we've got our cloud deployed, or our app deployed to cloud. Matt was already signed in, but if you are not signed in, you can do spin cloud login. All it requires is a GitHub ID, and then you can run the spin cloud deploy. And yeah, that's all for a cloud deploy. Should we move on?
Yeah, or people a second for any questions about the Fermyon cloud deploy and that kind of thing. All right, we'll keep going. If you're just walking in, this is the Spin and Kubernetes workshop. So,
cool. So we'll move on to how do we run this in Kubernetes. So
do a quick show of hands and see how comfortable people are. If you are comfortable using kubectl, you raise your hand. Okay, and then, all right. If not, we'll walk through things carefully so that if Kubernetes is a thing you're still learning, we'll take it slow.
Yeah. So kind of going back to the plugin conversation that we had earlier, one of our developers has a plugin called Spin Plugin K8s, and this will just kind of help you stamp out like a new deployment file as well as like a Docker file. If you'd rather write them by hand as you follow along, that also works. So we'll just get this installed. Already installed.
And the reason why this one has that long GitHub URL is because this is how you add an add-on rather than a built-in plugin. Is you just tell it where to fetch its plugin description.
Yep. And then just to run kind of locally, we're using K3D here. And we're using an image for K3D that's located under the Deis Labs containerd wasm shims. So just a quick note on how this works in WebAssembly or in Kubernetes is that the folks at Deis Labs / Microsoft have written a WebAssembly shim on top of containerd. So in order to run WebAssembly applications natively as a container, containerd needs access to this shim. So that when it gets a request for a new pod, it will look up using the runtime class instead of using run C or crun, depending on where you're at. It will use the shim to be able to run that WebAssembly bytecode kind of more natively on your cluster. So the node needs to have that shim installed. An easy way to do it with K3D is to just give it this custom image. And then we'll go deploy that.
So K3D is an easy way to run a Kubernetes little microcluster locally. You could also do this with kind, I'm pretty sure. You'd have to know kind well enough to translate commands from K3D to kind, but that should work fine. I think Docker Kubernetes probably works if that's, but we're just using, so far what we've installed on this system, Docker Desktop, which has the Docker daemon in it, and K3D, which we got from wherever SUSE distributes K3D from. Rancher, or somewhere on Rancher blah, blah, blah. Homebrew probably is where I really installed it from.
Oh, so we'll just create our K3D cluster here. We can give it a sec.
How many nodes does it create by default? Just one?
Just one.
Okay.
One agent.
And while that's installing, so quickly the kind of theory behind this is you install your Kubernetes thing, and normally when you schedule a container, Kubernetes pipes all the way down to the container runtime and says, start me up a new container like this. What we're going to do is install an alternate runtime next to the container runtime that says when a WebAssembly file comes in, schedule that instead of the container. And that's essentially, we'll spin up our Kubernetes cluster, then install the runtime.
Cool. So our K3D cluster is up and running. The next thing that we need to do is wire up the runtime class, or the runtime that's installed on the node, so that when we go to deploy the pod, it's able to find the shim. So we're just going to create a YAML file called runtime class.yaml. And you should be able to find this in the workshop as well. So the name is technically not important. What is important is this handler, and it's set to spin. And there's a long description of why that has to be spin, and it's because containerd. Yeah. Anybody have questions on this portion of how to wire up runtime classes, shims, Kubernetes stuff? Cool. So we'll just apply that runtime class. Used my own aliases too.
Oh, sorry, I probably didn't export the alias on that one.
Great, so that's deployed. And then we'll use the K8's plugin that we downloaded earlier.
So really at this point, right, now that we've got the runtime class installed, Kubernetes is configured to run WebAssembly, right? There's not any other step there. So now we're really switching back over into taking the application we built and then creating the Kubernetes scaffolding to execute it inside of a Kubernetes cluster.
What's your Docker handle?
Technosophos. Technosophos.
Got it. So the first argument for this command is going to ask us for a namespace that's really just an OCI repository. I guess with new versions of Spin, we don't need the Docker build portion, do we?
Nope, no, not anymore.
That's right.
Yeah. And this probably, okay, so when you build a container image, you push it up to a container registry, an OCI registry like Docker Hub. What is GHCR? GitHub Container Registry.
Yep.
Any of these kinds of places, and it packs your Docker file system into an image, pushes it up to this container registry, and you can get it anywhere. WebAssembly actually uses the same style of registry. So you can push it into Docker Hub, you can push it into GHR, ACR, any of the container registries. And so what we're doing here is preparing to push an image out there and then set up our Kubernetes manifest so that Kubernetes can pull that image back into the Kubernetes cluster.
Yeah, so spin K8 scaffold will create a Docker file. Another way to deploy that or to create an OCI image and deploy it is spin registry push to Technosophos my application 1. Added a V. So this will build and push your WebAssembly app to an OCI compatible registry. In this case, it's Docker Hub. And the scaffolding that we did with the K8's plugin will create the deployment service to be able to run. I'm going to actually change this service from load balancer to cluster IP because getting load balancer to work on K3D is more difficult. Cool. And then, like we mentioned before, this is another important part of the deployment YAML under the pod spec, there is this runtime class field that will map to the runtime class that we applied before, which will map to the containerd shim handler. So we'll just apply this deployment. Cool. So we've got our deployment up and running. We've got a service going. Let's just do a port forward because it's cluster IP to be able to interact with it outside the cluster. Oops.
Oh, yep. Go ahead. Sure.
So when you do spin to run, instead of the running in the Rust binaries, it converts into WebAssembly and then runs those binaries.
Mm-hmm. Yeah, so I'll repeat the question. Is there more to it than that? Or? Okay, so I'll repeat the question since for the mic. So the question was, when you take the source language like Rust and you compile it, is it compiling the binary directly into WebAssembly? And the answer is yeah. And in the Rust ecosystem, the way we do it is Cargo. The Rust toolchain has a WebAssembly compiler. So let's see, what's the command to install it? Rust up target wasm32 wazi, and then you install that and it'll install the compiler backend. And then when you build, it can build into WebAssembly. Spin just basically wraps all of that so that you don't have to remember the commands that I obviously can't remember, and it'll compile it to WebAssembly for you using the Rust compiler. For the record, so languages like Rust and Go and C compile to a single binary, and Rust and Go in particular compile to static binaries. What happens when you do JavaScript? JavaScript runs in an interpreter, and because of the way that the language itself works, it has to be an interpreter. You can't necessarily pre-compile everything because runtime decisions are made. So when we build the TypeScript one into WebAssembly, what we're essentially doing is we're taking an interpreter and the source files, and we're compiling, we're running the interpreter, loading the source files, and then compiling that whole thing into a big WebAssembly blob that is essentially the interpreter with the preloaded source. And then when it runs, you're just interpreting the JavaScript source as it goes. So it's a little bit different than sort of your normal way of running a regular binary application, but the performance is actually really good in WebAssembly. So with Rust, you tend to see a tiny bit of a performance hit because you have a virtual machine where there wasn't a virtual machine before. But with JavaScript, you tend to see a little tiny bit of a performance boost because you can pre-optimize things so that you don't have to do ad hoc loading. You load up, start the interpreter, and then freeze that whole thing as the WebAssembly binary.
Python the same way.
Python is the same way.
Faster.
Yeah. I wouldn't say a lot faster, but it's faster. Yeah.
Let's say you have two situations.
I'll come to you in just a second. Yeah.
One is like you have the container that only runs the Rust binary,
Mm-hmm.
and then you have another container that runs the same code, but has the WebAssembly compiled. And if you run both containers into the same Kubernetes environment, have you guys done the benchmarking difference between?
Yeah. So the question was, have we tested the native binaries versus and so this is where things get a little nuanced because container doesn't add too much in the way of per request overhead. But startup is really slow on a container. So you get about 12 seconds of startup time for a container. For WebAssembly, you get 1 millisecond of startup time for the WebAssembly one, which is what makes it really good for this kind of serverless workload. So if what you want to do is start something, run it to completion, and shut it down, you want something with a runtime profile of WebAssembly because the startup and shutdown speed is very, very fast. The runtime speed is just slightly slower than what you would get in a container. With some languages like Rust, it's more noticeable than other languages like JavaScript where you've got an interpreter. Long-running processes, you're almost always going to get a benefit from running it inside of a container as a raw native binary. So if you want to run something that's going to be up, milliseconds to hours, WebAssembly is a good candidate. If you're talking about like hours up to days, months, quarters, whatever, then you really probably are thinking containers right now, because the runtime, because the startup speed doesn't matter anymore at that point, right? You're running it for a long period of time. Then you're optimizing for runtime speed, and you're always going to get slightly better runtime speed when you can compile things all the way down to native and have them execute.
Just to verify, if something runs for like less than 5 seconds, you're saying you don't have to run the container, just do it and run away at the same time?
Yeah. Yeah. So the question was, so if it's running for like 5 seconds, are you starting up a container? And we're not starting up a container. It's just directly running the WebAssembly code. So if architecturally speaking, right, you in the bottom of Kubernetes, you have containerd, and containerd is responsible for starting up a container and running it. What we installed behind the scenes here as we were installing is what it was doing was installing a second runtime down here, the spin runtime. That executes WebAssembly. So now the request comes down and it says, is it a WebAssembly file or is it a container? It's a container, so run it on a container runtime like Moby or something. Is it a WebAssembly? Yes. Okay, then run it on spin. And so they're actually running in parallel at the very lowest level. And they're both packed as container, as images, as OCI images, but one's a container and one's just a WebAssembly binary.
Is that only possible in your platform where I can go do the same AWS cluster?
So you need a WebAssembly runtime, right? But yes, you can run them. So Azure, for example, has spin built in, so you can run it there. Right now, Civo is announcing in another room that they're adding WebAssembly support inside of theirs. So at some point, much of this setup, all of this setup that we're walking through here won't be necessary because all the Kubernetes clusters will already have that WASM runtime class. And you'll be able to just declare your pod, point it to say this is a WebAssembly pod instead of or this is a WebAssembly image instead of a container image, and it'll schedule everything for you. We have also, the way I'm saying it doesn't make it totally clear, so let me say it this way. It is possible to run a container and a WebAssembly module in the same pod in Kubernetes. So you can have multiple images in a pod. You can run one in WebAssembly and one in as a container, which is really cool if you're using something like sidecar thing like Dapper, where there's an HTTP interface from one thing to another thing. You can have one thing be a WebAssembly and the other thing be the Dapper data source, and then you can talk back and forth. So when you run these things in Kubernetes, you actually are getting a lot of the benefits of Kubernetes. That was kind of a long answer. Did I get to the gist of what you were asking? And then you had a question?
Well, based on what you had at least first started with, can you talk about how mscripten fits into that?
Yes, so mscripten is another WebAssembly runtime that is, so there, again, WebAssembly is a standard. And so as a standard, you can have multiple different implementations of it. Mscripten is a really amazing C++ based runtime. Who maintains it? Do you remember? Is it Google? There's an mscripten project. And it uses the V8, uses a lot of the V8 infrastructure. Another one is Wasm Edge, which is sort of an LLM-oriented one, so it's used a lot for inferencing and things like that. There's actually, if you're interested in LLM stuff, Michael Yuan, who created Wasm Edge, is speaking either this afternoon or tomorrow afternoon, and that's another good one. But Wasm Edge does a lot of WebAssembly directly. Yeah, that's part of CNCF. And then Wasmtime is another one that's created by the Bytecode Alliance, which is sort of one of the like CNCF for the WebAssembly ecosystem, or OCI for the WebAssembly ecosystem. They created one called Wasmtime. Wasmtime is the one we use. And so inside of Spin, you can find the Wasmtime engine, and it's doing them. So mscripten, Wasm Edge, Wasmtime, a couple others, they all kind of fit in that same space as being an implementation of the WebAssembly core, plus there are several different add-on WebAssembly specifications. And so all of these are governed by W3, which means one of them will put forward a candidate proposal and then implement it, and then others will start implementing it. So they're a little bit uneven in the sense that, like, mscripten had the new garbage collector a lot faster than the others. Wasmtime still doesn't have the new garbage collector because they go a little bit unevenly as the specifications kind of iron out. It's very much like browsers, where one browser gets it, and for 6 months to a year and a half, only that browser has it, and then all of a sudden all the browsers have it. WebAssembly kind of works the same way because it's standardized in the fashion. So essentially, you got a long-term choice and a short-term choice when you're picking your WebAssembly ones. And we chose Wasmtime as our engine because it's the one that's most focused on running components, the component stuff that you and I were talking about a minute ago. It's the most focused on that one, and that's the story we think is going to change the way developers write code over time. So again, long explanation, but I hope that got to the gist of your question. Okay. All right. We ready to go back and?
Yeah.
Right.
So we did the port forward, and then while Matt was talking, I did a couple of curls if you're watching the screen. And we've got 20 minutes left, so we'll try to, or is it 10?
I think we have till 3. We have till 3?
Cool.
Yeah, I think we do.
Yeah.
So 3:10. We have loads of time.
Loads of
I can
time.
talk a whole lot.
A whole lot of long-winded explanations coming at you. Cool. So
So you were, by the way, so you just, when you opened up the network connection, you did a port forward out of the cluster to map it to a local port?
yes.
Okay.
Yeah, and that's because the service that I used was a cluster IP, so not accessible. Load balancer, for me at least with K3D, was kind of difficult to set up. So because it wants to provision an IP address. So yeah, I just did a little cleanup, cleaned up the K3D cluster. You can leave it around if you want to keep playing with it.
Hey, do you want to pull up the pod or the deployment definition and show where in the deployment we tell it it's a WebAssembly binary? Since that'll answer directly. Yeah, so there's our spec for our containers, and you can see in there we tell it to use a particular runtime class. How do we do that? Is it with the new stuff that you did Dapper sidecars? How did you do that?
Do what exactly?
So you were using an image, a container image, and a WebAssembly in the same pod, right?
Yeah, so the containerd shim, if it looks at the OCI image, and so essentially it looks for the platform in the manifest of the OCI
Gotcha.
manifest. So if it sees WasM as the platform, it will run the WebAssembly. If it sees anything else, it'll forward it on to the regular containerd shim.
Okay. So it's actually containerd that's smart enough to do all of that?
Yep.
Okay. This, by the way, is a good, I'm going to editorialize because this is what I do. This is a good testament to how flexible Kubernetes is, that you can just kind of add a completely different runtime, and it just sort of wires up with all the things in Kubernetes. Makes us look like we did a lot of work, when in fact it's just the way Kubernetes works that makes this all fairly easy to configure. Sure, thanks again. We're going to do the LLM one tomorrow too, and I'll show some examples of inferencing there. So if that's your thing, I'd love to see you there.
Thank you.
Cool. So now we'll go through and get it running on Civo Kubernetes. So if you have a Civo account already, and if you have the CLI installed, you can do Civo Kubernetes create with a name. And then after that kind of initializes, you can run a Civo Kubernetes config with the name and then save, and that'll update your kube config. One thing to note on this is if you're on the UT guest Wi-Fi, they are blocking port 6443, so you'll either need a VPN or VPN. I think there's also some Ethernet ports around here as well. Sorry, say that again? Hotspot to your phone.
Yeah, that was what I linked it to my phone as a hotspot to get around the
Conference Wi-Fi is always awesome. My favorite thing. Cool. So we already set up a Civo Kubernetes cluster, and we just updated the config to use that. We'll switch the context so that we're not still pointing at the K3D cluster. And there we're just able to list out the nodes. So we know we have a good connection.
So now this is the part where things are changing with Civo. So right now, when we created that Kubernetes cluster, it doesn't have WebAssembly support by default. I am told that about a half an hour ago in another session going on concurrently, they mentioned that they're adding a WebAssembly runtime into Kubernetes itself. So we're about to install some stuff through a program called kwasm. Some of this stuff won't even be necessary within the next few months, if not sooner. So really exciting, but we might be the last ones who have to install this one this way today.
Yeah, so kwasm is just an operator that essentially does what was already built into the K3D image, and it will run a pod on each of the nodes, essentially a daemon set that copies that shim onto your node, updates the containerd config, and then restarts containerd. And then when you kind of scale out your cluster, new nodes will also have that shim already installed and be ready to run WebAssembly. So we've already run through these steps on our cluster, but if you have Helm installed, Helm repo add kwasm, and there should be links up here as well if you wanted to go through the kwasm docs, and then a Helm install for kwasm after that. Depending on the Helm values, I believe, there's two modes. So one where it will automatically provision the shim onto new nodes. Another is where you have to manually annotate nodes to be able to have that containerd shim supported. So we've already run through these steps on our cluster. And if you guys have any questions or run into any issues, just raise your hand.
And I think to get here, you need a Civo account, and then you have to download the Civo client, right, to do the Civo Kubernetes commands.
Yeah, you can also use their dashboard.
Oh, that's true. Yeah, you can. And then install your credentials through the dashboard. Yep.
Mm-hmm. So just checking out the kwasm operator, see if everything is up and running. And this is actually what you want to see, is these jobs that get completed. So those completed pods just mean the job ran on that specific node. And this operator pod is the one that actually listens for new nodes and runs the new jobs on the new nodes.
Part of the reason we didn't have to use kwasm on K3D is because it already has the runtime in the base image, right?
Correct.
And so it's automatically giving you the spin runtime.
Mm-hmm. Yeah, since K3D is just a Docker container, a couple of Docker containers running on whatever Docker host you have, you're able to just create a new Docker image using like the K3D base image and copy in that containerd shim, and then it's already set up and working for you. So if you're in something like EKS where you have control over like your AMIs or your node images, that's another way to do it, where you wouldn't actually need to run some sort of installer.
And I think the interesting story that we're not saying out loud is basically that right now, we've got Spin, we've got these runtimes, we've got WASM Edge, all these WebAssembly runtimes, And we've shown the value of these things to do things like with spin serverless computing, right? Right now, all of this is starting to ripple its way through the Kubernetes ecosystem. And some like K3D was a very early adopter, so they added a lot more of the tooling very early. AKS, the Azure Kubernetes Service, Civo, they're all adding these things very early. Others, they don't have support for it yet, like EKS. And so KWASM is a good stopgap for installing onto those until they start providing WebAssembly runtimes. So you probably will see over the remainder of 2024, fewer and fewer of the Kubernetes setups are going to require this kind of multi-step setup that we're doing today. And more of them are going to be like, oh yeah, you install this runtime class and you just start installing things and that's all it takes. So it's a very exciting time for us because exciting in the sense that it's really cool to see this stuff gain adoption, and exciting in the stressful sense in which we are always rewriting our documentation to go, okay, well now you have to do this over here and this over here. Okay, now this one moved over here, and but it'll be great. I think by the end of the year, the vast majority, if not all, of the major Kubernetes providers will have WebAssembly support built in.
So at this point, we've got our Civo cluster created. We've got the Shim installed. And then we're just going to go through and apply the same deployment that we had locally to our Civo cluster. And then got the terminal split here. So on one side, you can see how quickly they kind of go from, scheduled to running. Oh, image pull. There we go.
Oh, wow. Why were they taking me so much longer today? Because of the network?
Yeah, it had an image pull issue.
Yeah, okay.
So cool. Got those up and running. Part of this is also an ingress, so we don't have to do the
port forwarding stuff.
I think. Probably just HTTP.
And there it is, our 404 page not found, just like we wrote it in the email. That's what I'm going to do. I'm going to change all of mine from hello world to 404 page not found, and then when my demo breaks, nobody will know.
in the ingress, there's a path to my application, so that's probably what.
Yeah. Huh?
That system developer design interview.
Ways to pass your programming interview.
Cool.
Oh, there you go.
So that should be it. I just didn't put the path on there. So there you go. WebAssembly on CivoNet on Civo Kubernetes.
Yep. And again, that story is getting easier as we are in here talking. So let's see. So we started out, we did the spin application and created that really quickly, the spin new, spin build, and then ran it locally with spin up. We skipped over the Docker thing, and we can talk through that a little bit. But so we did that one first, the local, running it locally. You can actually take spin and you can put it anywhere from Raspberry Pi to plain old ordinary VM somewhere, and you can use that to run things directly if you want to, right? So spin itself is one way to run these things. Then we looked at deploying to Fermyon Cloud, which is just Fermyon's kind of hosted version. All of this runs part of Fermyon. And Fermyon Cloud is a little bit hybrid. Part of that runs on Civo. We're very happy with Civo, and tomorrow we'll talk about the GPUs. So run it locally, run it on Fermyon Cloud. Then we started talking about the Kubernetes path. And we did it on a local Kubernetes cluster with K3D. Then we did it here on Civo with Civo's Kubernetes. We skipped over one in the middle, and that is that Docker itself supports directly running WebAssembly inside of Docker Desktop. we don't necessarily have to show it, but we can talk through kind of how that, you want to talk through it, show it, whatever you feel comfortable with.
Well, part of the plugin from earlier where we ran a spin K8 scaffold, it also created this Docker file, really basic Docker file. The only thing you need in there is a spin toml, which is the application manifest. That's how Spin knows how to wire up the HTTP routes. And then you'll need the WASM files in there. And this is just a Scratch container, so there's no kind of base layer of the operating system aside from whatever's in Scratch. So there's nothing really there for an operating system to start up. And then to actually build this Docker file, you do need BuildX installed. So you'll have to grab that or enable that if you haven't yet. I think it's mostly enabled by default now. And then the other things you'll need to do, if you open up Docker Desktop, depending on your version, they recently changed this in like 4.2.7, so mine looks a little different. In 4.2.6, like if you're completely up to date with Docker Desktop, there will be use containerd to pull artifacts on the general page. On this version, it should be under features in development. So settings in the top right, features in development, use containerd, so for pulling and storing images. So you want to check that one and then hit apply and restart. And it kind of depends on your version of Docker Desktop. They've improved the experience kind of as they've just improved the WebAssembly story in general. So hit the first check mark of use containerd, apply and restart, and then go hit the enable WASM feature flag, and then hit apply and restart.
So is that to use it as in larger aggregation?
This is just like if you're really comfortable and if you want to use like Docker Desktop locally to run it. The startup time? Good question.
It's pretty much about the same. So what it's doing is basically the same thing Kubernetes is doing. It's installing Spin as an alternative containerd backend, and when it detects a WASM file, it's executing it directly in WebAssembly and not in a container. So the funny thing is, Docker, you end up wrapping it in a Scratch container so that it can be extracted and dropped back in. So the Scratch container is basically just acting like a tarball effectively for your WebAssembly binary. And I don't know that they're going to leave it that way. We were pretty close with Docker on this stuff, and I think now that everybody else is just dealing with the raw WebAssemblies and things like that, I think they'll probably follow along, but I'm not sure. You might know better than I do at this point.
Yeah, I think.
Or does everybody pack it in the Scratch?
It might end up in a Docker Desktop extension.
Yeah.
The issue with it right now is that every time the Shim gets updated, which at this point is like every month,
yeah,
Docker has to go update Docker Desktop and push out a new version in order to support that new version in Docker Desktop. So I think talking to the Docker folks, they were looking at taking that piece at least and making it into an extension, something that's that you can update.
Yes. Yep. Yeah, you can use them inside of Compose files. It's actually a really pleasant experience. At DockerCon last year, I did one where I built a little AI crossword solving helper and packaged that up using a Compose file, pushed it into Docker Desktop, and it's so slick. They did such a good job on that. It's like really pleasant developer experience. A funny thing is, so when we're running Spin, we're running it locally, not in a virtual machine container or anything like that. So it's building natively on Mac OS with an M1 ARM style architecture. So we compiled the binary on that system. We moved it to K3D is running a Linux operating system, also on ARM, but we didn't recompile it, right? Then we pushed it out to Civo, which is running Linux Intel. And there's no reason you couldn't run it on a Windows node. But that's one of the nice things about this way of building apps is you don't have to keep tweaking things for the deployment architecture because WebAssembly is architecture neutral. So you can build comfortably on your Windows Intel machine and deploy onto Mac OS ARM or onto Linux, whatever, and it just works. It makes it very easy to move functions around. So imagine a case where you need to use deploy the same application to like an edge node running some exotic thing out here and a data center node running Windows Intel here. You can deploy the same application and not have to rebuild it or make any changes whatsoever, because that's just one of the virtues of the WebAssembly format versus the Docker binary format where you'd have to change the Docker file, change your libraries, sometimes rewrite portions of your code depending on how the I/O works or what operating system. And so one of the virtues of WebAssembly, again, coming from its heritage in the browser, is it does actually run anywhere.
So about to mention the Fermyon platform that's hosted. Is that still a thing?
So Fermyon platform, we didn't talk about that at all, did we? In addition to running in Kubernetes, Spin can also run inside of Nomad, which is HashiCorp's scheduler, and use Consul and Vault and Terraform. And so Fermyon platform is a way of installing that particular stack, where you just get a Terraform and you apply the Terraform and you get HashiCorp worker nodes and Consul and Vault, and everything is kind of set up there. That is actually what Fermyon Cloud, well, we run sort of a big version of Fermyon platform. So Fermyon Cloud is actually not even running on Kubernetes, it's running on Nomad. And again, you know, the main difference is how you orchestrate things between Nomad and Kubernetes. The main difference is how you orchestrate things. When it comes to the application, as long as the application can get its files and get its sockets and things like that, it doesn't care where it's running. But yeah, we still maintain Fermyon platform for the HashiCorp world in addition to Kubernetes.
Yeah, so to build this all as like a Docker file, just kind of walk through different ways to build it. It's just Docker build x build. The important piece here is, well, two important pieces, is setting the platform to WASM. That's how it is able to look up the containerd shim and actually run. And then the other thing that you'll need, I think you'll still need it, is setting provenance to false. That's because WASM wasn't built into BuildX as like a signed platform. So that's why you'll need to set provenance equals false, because the Docker manifest thinks it's unsigned. So after that, you just set the tag, build it in less than a second. Because you're really just copying files into a tarball. And then from there, if you wanted to run it on Docker Desktop, look up the incantation here. I'm just going to type it out. Depending on which version of Docker Desktop you have, when you go to run it, you'll of course need the WASM set as a platform. The runtime is how Docker Desktop looks up the runtime shim, and depending on which version of Docker Desktop you'll have, it'll either be IO, containerd, spin v1 or v2, because like we kind of mentioned earlier, different versions of Docker Desktop ship with different versions of the shim kind of built in. So we'll try v1 first.
This is all Justin's very kind way of saying, Matt, you really should have updated Docker Desktop before we got on it. I'm like 3 versions behind. Yeah, so we use the Docker tool chain underneath the hood for all the credentialing and everything. So yeah, you can use a private registry in addition to a public one. Again, this is the nice thing about working in an existing ecosystem, is that so much of the tooling is built to be so flexible that we just call out to existing tools and let it do all the work for us. Signing and stuff like that, you can use cosign or any of those signing tools to sign and verify WebAssembly, just like Docker images. And neither us nor them made any changes to make that happen. It just once you invest in the ecosystem, you get the returns of the ecosystem, and the Kubernetes ecosystem has been really great to work in.
So the first time I tried to run it, Docker got mad because I didn't set an entry point in this Docker file in our deploy.yaml. That was one thing. One difference here is that we set the command. This can be pretty much anything. It doesn't really matter because the container dshim just ignores it. It's just that Docker run requires it. So if we look, yeah.
Yeah, sorry, I should have updated my Docker desktop before having you demo on my laptop.
So we'll try again with v2 because it looks like that container shut down right away. Nope. So now it's really just a debugging because Matt's Docker desktop is really old.
Yeah.
So if you have any questions,
but trust us, if you're using the updated Docker desktop, yeah. So we've got about 10-15 minutes left in the room, so we're happy to answer questions from here on out. Yep.
Sorry, I should have been late.
Oh, no worries.
You're calling it the booth is mentioning something about like the Lambda experience.
Yeah.
Is that part of your run? That part of Kubernetes or where with?
Yeah. Here, you want to pull up the code again, and we'll go all the way back to so essentially, what's happening with Spin behind the scenes is Spin is doing two things. It's starting up a listener that listens on a port for inbound connections, and then it's got some number of WebAssembly modules that it's mapping requests to. So request comes in, it loads that WebAssembly module, passes on the HTTP request, waits for the response, and then shuts down that WebAssembly module. So if we look at the index.ts, which is the second tab up there, this is a complete Spin application, right? So there's no main, there's no server, nothing like that. There's just a function called handle request. And based on the object type and everything like that, the runtime knows, okay, this is an entry point. So when I get a request, I hand it off to handle request, I give it the request, wait for the response, and that's all there is to it. And the same thing is true for Rust, for Python. You can do a Python app if you want real quick. For Python, you don't have to, I'm just randomly thinking of things to, but it'll work for any of those kinds of things. So you get essentially that Lambda experience. So when you deploy it to Fermyon Cloud instead of Kubernetes, you're just pushing that WebAssembly runtime up there. We're running, we were talking about it a little earlier, we're running Nomad on that one instead of Kubernetes, but we're running around 1,600 user-supplied WebAssembly applications per node on the cluster. And the VM size for those nodes is a 2XL. So it's a fairly modest VM size, but it can still run around 1,600. And part of that is because it's using that serverless style where the request comes in, it executes it, shuts it down, and so you can run a whole bunch of them in parallel. So it scales incredibly well if you have a lot of serverless functions, and you can actually save quite a bit of money when you say you got 100 serverless functions and all of those are getting called in sort of a choppy sort of way. Then this is very effectively sharing the CPU and memory across those compared to, say, the older architectures where they would spin up and pre-warm a VM or a container per function, right? So then you get a lot of overhead just keeping that VM or container sitting idle. That's what we get rid of here. And then because of the 1 millisecond cold start time on WebAssembly, you end up being able to handle these requests very, very fast. Yep.
Quick question about that, actually. So for these WASM applications, I guess, like, I guess you're not using Kubernetes, but do you use kind of like the equivalent of like requests and limits for each one of these?
Yeah.
They start up, and if so, like, what kind of values are you setting to be able to get like 1600 on a node?
What are our defaults on that one? So we've got a timeout set. The most important one is the timeout on how long something can run. And I told somebody earlier it was 15 minutes. I think it's actually 5 minutes is the maximum time. What you tend to see is that the binary sizes tend to be 5 meg, 10 meg, maybe 20 meg at the very upper bound. Like Python, sometimes you start pushing the 20 meg one. So runtime wise, you still have fairly modest requirements there. When you're in Kubernetes, you can set them per application. I forget what we've set, but it's I think it's in the 20 to 50 meg range there. We run Fermyon.com on top of on top of Fermyon Cloud, and it's a very bulky website. And so we figure if we can run our own gigantic website on it, then probably we're doing okay for what people do. There is a little caveat here so WebAssembly's binary format is very platform neutral, very easy to move around, and you take a performance hit for that. We were talking about that a little bit earlier. When you deploy an application, once it gets scheduled to a node, you know for sure what the processor architecture is and for sure what the operating system is. And so there's a project that's part of the WebAssembly ecosystem called Wiser that No, it's part of Wasmtime. I guess it's part of Wasmtime. You can AOT compile, so you can ahead of time compile it directly to the architecture there and retain all the security properties, but have it start up even faster. So we enabled that on Fermyon Cloud, and we're working on enabling that on Kubernetes too. And that means that effectively you're down, that's how we got down from 10 milliseconds to 1 millisecond. And then as we've learned to tune it, we're actually getting down into around the half a millisecond cold start time. And pretty soon we're going to hit some limits, right? Because the security sandbox itself is going to take a hit over just a native binary. But the better we get at stuff like the AOT compiling, then the closer we get to a native experience when it comes to the runtime. But you still get all the portability because you're really just dealing with cached native binaries that have, per worker node. So it's actually a lot of fun to work on this stuff. There's just so much cool technology evolving in this space. Did I get your question? Yeah. I have a tendency to start to answer the question and then get sidetracked by my own random train of thought. So.
So there's we've got the JavaScript, V8 JavaScript engine support.
Mm-hmm.
Now an Nginx unit.
Yep.
Unit which has an application server support.
Yep.
CGI, JavaScript, and Awesome.
Yep. Spin applications too. Yeah. 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 Because a spin application is a WASM application that just expects that you also have key values.
Like you've got routers.
Mm-hmm.
What are some of the directions you see this going use cases?
Yeah, that's a great question for this point. Where is all of this going, right? We're starting to see implementations crop up here and there. And we've been talking a lot about the serverless function method because that's the thing we think WebAssembly adds immediate value there. We took a little detour into components early on, but I'll kind of reiterate at a high level what that is. So with a component model, you should be able to take libraries and compile those into WebAssembly, and then you can link those. So you can link cross languages. So for example, we won't have to write a YAML parser in every single language under the sun. We could write it in one very high performance language like Rust or C or something like that, and then link it from JavaScript, from TypeScript, from Ruby, from Python. That's where I think the really interesting stuff is going, right? So as we see runtimes crop up in various places, Shopify added it so that you can write a Shopify extension to your store and compile it to WebAssembly and run it there. That's a really cool way of building a plugin mechanism, right? So we've got serverless functions, we've got plugin mechanisms, we've got the in-browser stuff, IoT. We're starting to see a lot of activity in the IoT space because the runtime is so small that you can put it in very tiny devices and have them perform quite well. So we're seeing the runtime sort of get spread out into all these different places, but it's the component model, I think, is where I would bet, the future is going, right? Because if we can start building applications that way, where no longer are we re-implementing the same feature in every language, where we can, add those shims in and plug in at runtime backends and processing libraries and things like that, then it'll change the way that we can develop. We'll be a lot more effective as developers because instead of re-implementing and fixing bugs in every language, we'll start to be able to use common versions of the same library and share those broadly. So I'm really excited in the fact that I think that's going to kind of change the way we write code. And so when we focus a lot on developer experience for us, right? The idea of spin is you should be able to spin build regardless of the language and it'll compile it for you. As the component stuff is maturing, spin will have component commands built in that'll allow you to tell it how you link things together. That's where I think the really interesting stuff will be over the long term. And for us, serverless functions are sort of our passion of how we want to do this for server side, and where we've seen lots of people spend a lot of money on technologies like Lambda and have to manage it outside of Kubernetes, and we think we can kind of create a better developer experience and save money for people and boost their efficiency at the same time. But this component stuff is so cool. It's just going to change the way we do a lot of software composition, and that's where I think things are going. So, Nginx added component support. We've worked with that team to get WASM-time component support into Unit, because the more runtimes that support these kinds of features, the faster we'll be able to kickstart that process of creating these new kinds of WebAssembly libraries. So I think a year and a half, 2 years from now, the conversation will have a lot more to do with running distributed applications and moving components from one place to another depending on the proximity to the user or something like that, right? Because that'll be level 2 of this WebAssembly ecosystem we're building. And I could probably talk about that for another 15 minutes, but, but I'll stop there. We got a couple minutes left. Any other questions or comments? Tomorrow we'll do, we have a 30-minute session, much shorter and very concise, just covering LLM inferencing with WebAssembly. And we'll use the Llama 2, and we'll talk about Civo Deep Green GPUs and how we are working on heating a swimming pool somewhere in the UK by running LLM workloads. So it's a great world we live in. As technologists, we have the best job ever. All right, with that, we'll hang around for a couple more minutes, but thank you again for coming and trying this out with us.